Good morning, everyone, and welcome to our monthly Hazardous Webinar series, where we take a closer look at one of Natural Hazards Research Australia's research projects, its findings, and how it will be translated into practice with members of the project team and the people who will use the research. My name is Nicola Moore, and I'm one of the node research managers with the Centre, and I'm based up in our Brisbane office. Before we commence, I'd like to acknowledge that we're all gathered from across a range of different Aboriginal lands today, and I'm a guest here on Yagara Turrbal lands in Meanjin, Brisbane, as I am wherever I walk in Australia because sovereignty has never been ceded. And I pay my respects to the Yagara Turrbal elders, past, present, and emerging, and also to any First Nations people joining us online today. These lands and waters across our country have always been places of teaching, research, and learning. First Nations people have long looked after and cared for country as kin and continue to do so today, and we can all play a role in dismantling the ongoing processes of colonisation by supporting Aboriginal and non-Aboriginal people on this journey. After all, we all share the same fundamental goal, and that is resilient and sustainable landscapes and communities, and everything in between. So thank you all for joining us today. Questions will be answered at the end of the formal panel presentation. So please, as we go along through the presentations, add your questions into the Q&A function and make sure you specify who your question is for so that we can get to them in the last 15 minutes of today's session. It's my pleasure to introduce today's three panellists to you. Chief Superintendent Laurence McCoy is the Manager Predictive Services in the Community Resilience Unit with the New South Wales Rural Fire Service. He holds tertiary qualifications in applied science and leadership and management, in addition to numerous firefighting training and environmental management qualifications. Laurence has significant firefighting experience in a range of roles and has been deployed to major incidences within New South Wales and around the nation, including Black Summer in New South Wales, the Black Saturday event in Victoria, multiple deployments to Tasmania and Queensland, and 2 overseas deployments to Canada. After spending time in the Northern Beaches and Far North Coast districts, he was seconded to the New South Wales Rural Fire Service headquarters to project manage the establishment of a fire behaviour analysis and smoke modelling capability within the New South Wales Rural Fire Service, and has now progressed to lead the New South Wales RFS Predictive Services Unit. Great to have Laurence with us today. Agnes Kristina is the Senior Environmental Officer with the Department of Fire and Emergency Services in Western Australia, working within the Rural Fire Division's Bushfire Technical Services section. She has over 10 years' experience with DFES, supporting bushfire management through the application of science and technology. Agnes's work focuses on translating research into operational tools and capabilities, including satellite-derived grassland curing, spinifex root zone soil moisture studies, and facilitating the operational deployment of portable weather stations across the state. During bushfire season, Agnes undertakes the role of State Fire Behaviour Analyst in the State Operations Centre and serves in situation and analysis roles within Level 2 incident management teams. And prior to her work with DFES, Agnes worked as a remote sensing officer in the Firewatch team at Langate's Satellite Remote Sensing Services. Combined with her academic background, she brings over 20 years' experience in the integration of geographic information systems, GIS, and satellite technologies, with a focus on applying remotely sensed data to bushfire detection and environmental impact analysis. Awesome to have you with us today, Agnes. And Dr. Mika Peace. Mika is a fire weather researcher in the high impact weather team of the Bureau of Meteorology's research group. Her research expertise focuses on bushfire case studies and running high-resolution fire atmosphere coupled simulations. In her research, Mika partners with fire agencies and land management groups to develop understanding of how the atmosphere in 3 dimensions drives fire behaviour. The Access Fire modelling system Dr. Peace uses has extended the Bureau's weather modelling capability to explore and document fire and atmosphere interactions that occur during major bushfires, and her research findings are shared with practitioners to help predict where and how a fire will spread and what fire behaviour is likely to occur. During high-impact weather situations, Mika often takes an operational role briefing key stakeholders on the weather situation and assessing the likely impacts on the community. She regularly presents nationally and internationally at conferences and workshops, invited media interviews, STEM events in schools, and science events in the community. So today's webinar focuses on the Fire Case Studies project. This work has provided an opportunity to systematise and consolidate existing fire case study methodology developed within the Bureau's research team to enable quicker results in future with potential benefits, including faster responses to official inquiries. The project has delivered 2 detailed case studies of the New South Wales Lake Conjola Currowan fire of 2019 and the Wooroloo fire in Western Australia in 2021, exploring the meteorological conditions that led to extreme fire behaviour. So I'll now hand over to Laurence, Agnes and Mika to share their presentation. So over to you, Laurence.
Okay, so I'll kick off my presentation from an end user perspective, and thanks for that introduction, Nicola. So why case studies? And I'll why case studies from a New South Wales context, but generally more broadly. So weather, fuels and topography are key inputs into fire behaviour, and we know how variable weather can be. And we're seeing, with time and climate change, we're seeing an increasing severity to weather. This year in New South Wales, or Western New South Wales, we're still in the hottest periods on record. And it's this increasing severity of weather that's a key driver for the increase we have or we are seeing in extreme fire behaviour. So in 2019-20, we saw a 50% jump in the number of recorded fire-generated thunderstorm events from 60 to 89. And we also saw devastating, rare and unusual extreme fire behaviour in New South Wales, like fire-generated vortices, such as those that occurred at Green Valley, Talmomo, and other locations in New South Wales. And in these extreme and unusual circumstances, we understand what's happened, but sometimes we don't fully understand the mechanisms that are causing these unusual and extreme fire behaviour. So the Bureau, as we know, is a respected science-based organisation, and they've got a unique capacity to help us understand these events and to learn from them. And so historically, these case studies prepared by the Bureau of Meteorology have been so important for us in New South Wales. They've been used to support legal and coronial investigations, such as the 2019-20 inquiry, but also inform operational or executive or ministerial briefings, and to guide community information or public messaging. We also get to investigate and learn from these unusual fire weather and fire behaviour events, and we capture these lessons for the future so that we can learn, continue to learn. And so I think the benefits I've spoken about, some of those benefits, they're quite obvious, but through this through this project and other case studies, we've seen contribution to improvements in our understanding of the mechanisms that are driving extreme and unusual fire behaviour events. There's been training material developed, and you can see there some examples through this project where we've had training material produced from the case studies and the research that's been undertaken about extreme fire behaviour and and how fires interact with atmospheric boundary layers. For us as an agency, these case studies help us to inform policies, our procedures, some of the systems we use, and information that we display, and the decision support tools that we develop. And more critically, one of the benefits is that we see improvements to the science and innovation tools, and in particular through this project, improved use of new meteorological tools, but also the coupled fire behaviour modelling. So for us, the 2019-20 fire season was one of the worst New South Wales have ever experienced. We know that it came about after a period of prolonged drought and unprecedented weather conditions, and erratic fire behaviour resulted in tragic loss of 26 lives and nearly 2,500 homes across the state. One of the fires that occurred during 2019-20 was the Currowan fire, and the Lake Conjola fire was one of 9 fires that were amalgamated into the Currowan fire that burnt nearly, over 300,000 hectares. And so on New Year's Eve, 31st of December 2019, the Currowan fire, it escaped containment lines in the vicinity of Lake Conjola area, and it had significant impacts on communities of Yatta, Conjola Park and Lake Conjola. And we saw extreme fire behaviour during that event. And so as a result, we wanted to understand the mechanisms further driving that extreme fire behaviour, and we requested the Bureau undertake a case study as part of this project so that we can learn more about these mechanisms, and also we can advance new tools like the coupled fire atmospheric capability. So that's it from me. I'll hand over to Agnes now for further context from Western Australia.
Yeah, so good morning all. My fire case study will be on the Wooroloo bushfire that happened in Western Australia in February 2021. So before getting into Mika's key learnings from the end user perspective, I'll briefly outline the events on the day to provide you some context on the fire itself. So the fire started near Werribee Road, Wooroloo, and was reported at 12:02 p.m. The fire danger rating on that day was very high to severe, with total fire ban and harvest vehicle movement ban declared. By mid-afternoon, there were 500 firefighters and 95 vehicles involved in the firefighting effort, along with fixed-wing and rotary water bombers. And from the ground, erratic fire behaviour was reported, with rate of spread of 3 to 4 kilometre an hour and spot fires up to 500. However, then at 2300, emergency alert were issued as the fire intensity increased. And a couple of hours later, around 1 o'clock, 3.5 kilometre spotting was observed and threatening more properties. So there's a map to show the extent of fire. Most damage was done within 24 hours of ignition. The fire was 29 kilometres long, 7.6 kilometre wide, with a total of 10,750 hectares burnt within the Shire of Mundaring and City of Swan. And then the bottom right of your screen, you can see Himawari that captured at 1200 on the 1st of February, showing heat anomaly near ignition. So Himawari is a 2 kilometre resolution. So when it picks up heat anomaly quite obvious, then you know that the fire is quite intense. Just showing you the incident weather forecast. I was the state fire behaviour analyst then, and you can see when I saw the incident weather forecast updated twice, you can see it's not going to be a good day. As you can see, dew point here are all low, wind directions consistent, and wind speed are all consistent. And that is occurring during the day and night. And this is showing the simulation at 2:15, 5:15, and 11:15. Fire was burning in mostly forest and grassland vegetation. Simulation, fortunately, was less complex due to the consistent wind direction and speed, and there's a good alignment between the simulated fire and the observed fire extent. And also note that the simulation assumes no suppression or suppression is not successful. Fortunately, when rain was received on the weekend and fire was declared to be extinguished by Sunday, 7th of February. However, there was significant property loss and infrastructure damage, particularly from the first 24 hours, and the hardest hit area was Tilden Park, where 80% of the property were lost. And the estimated insurance loss of the Wooroloo bushfire was about 93 million. So what did we learn, and why case studies like what Mika has done really important? Well, definitely for this case, we understand that the 2021 Wooroloo bushfire was driven by extreme conditions, which is typical in Western Australia's summer, but made it worse by the extreme drought. And Mika's studies, data and science confirmed that what we observed during the incident, that it was wind-driven during the day and night. So with all this data and science and what we observed on the day, we could use access modelling to identify observation location that mostly accurate represent prevailing fire weather conditions that are consistent with bushfire assessment and methodologies, which can provide evidence-based scenario modelling for new developments, particularly in the planning stage. And that's for Western Australia, and we'll hand it over to Mika.
This is work that's been done by the High Impact Weather team at the Bureau of Meteorology. You've got the team names up there. I'd just like to thank NHRA, DFES, RFS and CFA, and also the satellite and radar research teams at the Bureau for supporting this work. Before we go into the two case studies, I want to talk a little bit about why we do case studies and what they are. So meteorological case studies are a detailed examination of a weather event. They tend to take a narrative form, and they document the features of extraordinary weather events to examine the causes and the impacts, and importantly, to present a scientifically plausible explanation for why events occurred. They're not acts of God. There's always a scientific explanation for what happened when we look at the data. Historically, research case studies, particularly at the Bureau, have taken a lot of time and effort, and that's because they typically leverage a lot of individual expertise and computational capacity, so they've come at a cost. The current NHRA project has really been about developing a framework for more rapid turnaround of case studies, using in particular the high resolution coupled fire atmosphere simulations with access fire, and also a range of observational data, particularly the radar data and the satellite data. So the objective of the project has really been to do case studies cheaper and faster, using the two examples as a template. Case studies are an evidence-based investigation, and the core aim is really to identify and then clearly document the physical processes that were responsible for extreme weather. Case studies draw heavily on scientific knowledge and also conceptual models, which we use a lot in meteorology, but they're not purely theoretical because they connect to real-world scenarios, and that approach really builds trust and relevance with practitioners. Visuals, such as the ones that I've got on the screen now, are a key feature of case studies, and that's not just because a picture speaks 1,000 words, but it's been shown in research that the use of images is really powerful for memory retention. Although case studies often have conclusions that are related to specific events, the findings can usually be generalised to other locations. Case studies a lot of the time use emerging computational capabilities and other technologies, so they provide a really valuable testbed for developing and evaluating new tools. And as we all know, the technological capabilities available are evolving really rapidly. So case studies present a mechanism to assess new tools and also assess their suitability for operational use. And as we heard from Laurence, they can either implicitly or explicitly make recommendations for improving operational processes and best practice, as well as policies and disaster management strategies. I think the people aspects of case studies are really interesting for a range of reasons. So during extreme weather events, we know that people make decisions under pressure and uncertainty, and these decisions are strongly influenced by prior learning and knowledge. There's a lot of evidence that post-event learning can improve decision-making in future events. And as we've already mentioned, learnings in the context of lived experience is really critical for practitioners rather than theoretical learning. For people conducting the research in case studies, it's a really valuable learning and development exercise, and it's meaningful, it's challenging, and it's really interesting work. So it contributes to job satisfaction and personal well-being. And as we're expecting in the future that AI is going to replace a lot of roles, case studies can offer really rewarding work and career opportunities for the next generation of scientists and practitioners. Also, research has shown that improved understanding of events can support psychological recovery from trauma. So reconciling what has happened can help people make sense of events. And this process can improve the mental health and also the well-being of those impacted. And that includes both first responders and affected communities. So investment in case studies is worthwhile. As we know, weather events are becoming more frequent, more intense and more complex with climate change. And we're seeing increasing impacts to communities, infrastructure and the EM sector. A key element of the case studies that we run here at the Bureau is the coupled fire atmosphere model Access Fire. And we've been using it for about 10 years now to really explore the processes and the fire and atmosphere interactions at major fire events. It is Australia's key operations and research weather and climate simulator access, coupled to a set of fire spread models. The fire spread models that we're using now in Access Fire are the same as what's in AFDRS, the Australian Fire Danger Rating System. And the bottom right image here shows the fuel grids that we've used for the Wooroloo simulations. With the coupled model, what happens is that the fire spread model and the atmospheric model interact at each time step. So the fire model calculates fuel burned and passes a heat and moisture flux to the atmospheric model at each time step, which means that at subsequent time steps, the atmospheric model, the winds in the atmospheric model respond to the heat fluxes, and then you've got a change in wind that goes back into the fire model at the next time step. So that's how it drives the coupling process. And that coupling can be turned off for non-fire cases. So we can run it either with a fire or without a fire quite easily. Usually in our simulations, we run 300 metre or 100 metre horizontal resolution. Just for comparison, our operational models are run at 1.5 kilometres. We use 140 vertical levels, and we usually do the output either at 10-minute or at 1-minute time steps. It's currently used for research only, but importantly for the access model, because the model framework is used extensively in Australia's operational weather prediction and also for our climate simulations, the model framework is familiar and the output is familiar to a wide range of users, including all of our practitioners. All right, on to the Wooroloo fire. So as we heard from Agnes, it was in February 2021, around about 50 kilometres northeast of Perth, so pretty close to the Perth area. And there was a real mosaic of fuel through the rural-urban interface. Nearly 11,000 hectares burned and 86 properties lost. You can see from the extended fire perimeter shown in the bottom right plot there that there was an extended period of easterly winds, not a lot of change in wind direction. And as Agnes said, the first 24 hours of the fire was really key. So we focused our studies on this, and this was when the fire tripled in size overnight. You can see in the top image there, the satellite hotspots for the first 2 days of the fire shown in yellow and red. The subsequent days are shown in green colours. So the yellow and red area is the area that we focused on for our simulations. And you can see from the bottom plot that there's a reasonably good match in terms of the fire perimeter. So the coloured isochrones in the bottom plot show hourly fire spread from our simulations, and we've got the grey and the black in there showing the topography. So when we do case studies, a lot of what we do is sort of setting the scene in terms of the meteorology of what was going on, and we use a combination of observations and NWP data to do this. So working around from the top left plot there, in the water vapour image from the Himawari satellite, we can see a really dry slot over Wooroloo in the water vapour. Down the bottom left in the MSLP chart, we can see a tropical cyclone over the Coral Sea, which is pretty typical to see a tropical cyclone over Northern Australia on a bad fire weather day. There's a really deep vertically stacked low over the Pilbara, and there's the ridge of high pressure in the Southern Ocean. And those two features produce a really tight pressure gradient along the coastal trough, which helps drive the easterly wind speeds offshore. On the top right there, that's the 300 hectopascal upper winds. Again, typical setup for a bad fire weather day with a ridge of high pressure with an upper ridge over central Australia and split flow over the Tasman Sea. And on the bottom right there, we've got the aerological diagram that was taken at Perth Airport in the morning, showing really dry air in the low levels and also a low level wind maximum. In the centre is the rolling green, which was the nearest automatic weather station data for the day. Really hot, dry air, temperatures pushing up 35, 40 degrees through the area, incredibly dry with dew point temperatures dropping below zero, particularly in the overnight period, and really persistent easterly flow in the winds with strong and gusty offshore winds. So a lot of the features that we'd really look for a bad fire weather day over the Perth area in southwest WA. Looking at the simulations that we ran, so the colour contours are showing the fire spread at hourly time intervals, and the white and grey and black colours are showing the topography. So we can see again that elongated fire perimeter in response to the really persistent easterly winds. You can see if you look at the pinky purpley coloured isochrones that we had fast fire spread in the overnight period, when the expectation, of course, is that fires are normally going to lie down, and it makes it easier to put suppression and containment efforts in place. That wasn't the case at this fire. The topography contours show the Perth Scarp and the coastal plain. So for those who aren't familiar with Perth, it's got sort of higher land to the west and to the east, and then the coastal plain to the west, with quite a sharp scarp, which helped drive some accelerated fire behaviour. And over the coastal plain, we can see a little bit of fingering in fire spread in response to some of the more urban fuels and some non-combustible grid cells in there. Okay, so these are the access fire simulations of the Wooroloo fire, showing the heat flux and the 10-metre winds, and you can quite clearly see the fire modified winds, particularly near the head fire. We can see in the simulations that the fire spread direction changes quite a bit in response to very subtle changes from southeast to northeast wind shifts. So although we had easterly winds, there is a bit of variation from a southeasterly to a northeasterly, and you can see the maximum heat flux around the perimeter adjusts in response to those wind changes. Now, those kinds of wind changes aren't necessarily always going to get captured on an operational forecast, but they can be important for positioning of assets and other fireground decisions. You can see that the background winds generally are around about the 10 to 20 kilometre an hour mark, particularly as we're looking now in the late afternoon, early evening period. But we can see that near the fire line, particularly near the head fire, we get winds at times reaching up to 80 to 100 kilometres an hour, which are much stronger than the winds that are close nearby. We can also see in the simulations that the wind direction varies by over 90 degrees at times in response to the fire modified winds. And you can see now that as we go into the evening period and towards midnight, we've got stronger winds, particularly along the scarp, which is what we'd expect to see with the downslope wind phenomenon. All right, this is the same data that we were just looking at before, but a slightly different colour scheme, just to highlight the variation in wind speed across the domain. So we've got around about 50 kilometres east to west on this domain, and the fire extent's around about 25 kilometres east to west. And if you look at the time step on the top corner there at 12:03 a.m, this is midnight, when fires are meant to be less active overnight, but as we heard, a really significant fire run occurred. So looking at the colour scheme on the winds, you can see that winds across the domain range from around about 10 to 20 kilometres an hour in those sort of orangey colours, up to 40 to 50 kilometres an hour, and then 50 to 60 kilometres an hour in the green and yellow near the active head fire. And then you've got pulses in those sort of black arrows getting up to 90 to 100 kilometres an hour. So different parts of the fire line are going to be experiencing different environmental winds. And of course, if we're issuing a forecast, we normally issue the forecast for where the fire started rather than where they're heading to. So you've got a really different wind regime from the fire's ignition point to where it actually gets to on the Perth Scarp in the overnight period. So the big challenge there for the operational teams, both the forecasters and the fire behaviour analysts, and also those on the fire ground, is what's the piece of information that you need on an operational forecast when you've got winds from 10 to 20 up to 90 to 100 kilometres an hour showing up on the high resolution simulations. What's the right information to provide? This is an absolutely fascinating close-up of the southern flank of the fire as it crosses the Swan River Valley at midnight. So in here, we are looking at every wind grid point at 100 metre resolution over a zoomed in part of the domain. We can see in the topography here that the white contours are showing us the Swan River Valley, which is north-south orientated at this point. So the white is the 50-metre contour and the black is 200-metre contour. So we don't have particularly high topography, but you've still got really significant wind effects occurring from just the topography, but also from the fire and atmosphere interactions. And again, this is around about midnight when we're expecting to see quiet fire behaviour in the overnight period. If you look closely at the detail of simulations, you can see light winds and even some westerly winds right down the bottom of the valley, very light winds in there. And then as we see the fire approach the ridge top, we've got this extremely strong easterly wind surge with the fire modified winds reaching 90 to 100 kilometres an hour. And for those who are familiar with the Bureau's operational products, all of this domain is around about 6 kilometres across. So it fits inside one of the grid cells for the ADFD or the METI grid boxes. So all of this detail process is happening inside the resolution of the data sets that are provided operationally. So the question, of course, is if you're doing a fire prediction or if you're doing a fire weather forecast for this fire, what's the number in terms of your wind speed that you put on the operational forecast? And what's the right number to use as input to fire predictions when you've got that kind of variability across a very small segment of fire line. The other thing I'd like to point out is that this is the first time that we've really looked at this kind of simulation of the 100-metre resolution in this kind of topography, and it's just absolutely remarkable detail. And a lot of people have really commented on the other applications and also the value of these kinds of simulations. So there's huge potential for these kinds of simulations to be used more widely across a range of sectors and applications in Australia, and I'll come back to that in a little while. We know that the overnight low-level jet was a driver of the overnight fire run, so we wanted to look at cross-sections to try and look at the structure of the jet a little bit more and how it was interacting with the fire plume. So the top inset box here, you can see a green line in there through the fire line. That's showing us the location of the cross-section that we're looking at in the main plot. And the main plot is a vertical cross-section of wind so that we can look at what's happening with the low-level jet and the fire. So we've got the black at the bottom of this main figure as the topography. You can see some coloured yellow and pink shading, which is where the active fire area is. And the main plot is showing us the wind speed, with the arrows showing us the wind direction. So you can see that the low-level jet is around about 200 metres above the surface, above the topography. So it's a really low feature. And in those pink and purple maximums, it's getting up around 25 metres per second, which is up around 90 kilometres an hour. So you've got 90 kilometres an hour of wind sitting just above the surface as this fire is moving through. So when the fire plume interacts with the jet, it brings the strong winds down to the back of the head fire, and it's not the much lighter surface winds that's then driving the overnight fire activity. It's those strong winds coming down in the low-level jet interacting with the fire plume that's producing accelerated fire spread overnight, particularly over the topography. And we've seen a number of fires now, which have seen accelerated overnight fire spread on the Scarp in Perth. This kind of setup happens quite frequently because of the way the pressure gradient works over Western Australia. But this kind of acceleration with low-level jets overnight also happens in other places. And it's been the reason for a number of overnight fire runs at impactful fires, not only in Australia, but around the world. So the Currowan fire was the case study that we did with RFS, which, as Laurence said, burnt over 300,000 hectares during Black Summer over several months. And on New Year's Eve, the Currowan fire spotted across the Princes Highway near Conjola. There were 89 homes destroyed and 3 fatalities. We can see on the RGB fire enhancement satellite loop here, which is an enhancement that picks out the active fire. It really illustrates the massive challenge that was faced by the emergency management sector on New Year's Eve in 2019, because we have multiple fires with really long perimeters burning during the night and during the day over southeastern Australia. And we can also see from this animation that we really lose situational awareness when we lose the satellite data and when cloud moves across and obscures the surface fire. The purple arrow in here shows the location of Conjola on the southern New South Wales coast, and there's a little cross marking the location of Conjola there. All right, the New Year's Eve forecast, the weather forecast was a bad fire weather day for several days out, with northwesterly winds ahead of a strong southerly wind change along the coast. RFS issued a red map fire prediction the day before, so on the 30th of December. And it shows that the fire was expected to remain west of the highway, and the main fire spread was expected to be further north near Nowra and very much under the influence of the southerly winds rather than the northwesterly winds ahead of the change. As we know, the fire crossed the 6-lane highway and impacted the communities of Lake Conjola and Conjola Park. Now, the image on the right there is the Sentinel image from the Copernicus satellite at 11:06 a.m. And you can see that the fire had already spotted east of the highway. So we can see some spot fires east of the highway in there. One of the queries from RFS when we were doing this case study is what the winds at the fireground were, because the winds that drove the fire spread didn't match either the forecasts or the local automatic weather station observations. And the Bureau had issued an incident weather forecast, but we were restricted in terms of capacity. So we were only issuing a set number of forecasts. And the forecast for the Currowan fire was located 40 kilometres to the north of Conjola, and it was further inland. So it was very different representation in terms of the weather to what was experienced on the coast further south. These are our half-hourly fire spread isochrones from the simulations using Access Fire. This domain is around about 15 by 15 kilometres. And the red initial fire line, which is at 9:51 a.m, which seems like an odd time, but it was taken from a line scan image that was taken at 9:51 a.m. and provided to us by RFS. There are a number of features of interest in here. One is that the individual fires, because there were a number of active sort of fire areas in the Conjola area, the individual fires all took fast runs at different time periods. And probably the best way to look at this is to look at the sort of central fire and the fast run that it did between 9:51 and 10:21, which was quite considerable, whereas the southern fires ran a lot less of a distance during that time period. So the different fires in pretty close proximity all took fast runs at different times. We can also see from the isochrones, and we'll see it again in a minute when we look at the animation, that there was coalescence between the individual fires, and that was partly supported by the fire modified winds. And one thing to note in particular, the southerly wind change produced really rapid spread at the southern fire at Yatta Yatta as the change went through. So the blue isochrone at 1:21, you can see how it's that the area around Yatta Yatta was burned really, really rapidly in that time between 12:51 and 1:21, and we'll look at that in a little bit more detail. So these are the Access Fire simulations of the Currowan fire. As I said, the initial fire boundary was from the 9:51 a.m. line scan. We're looking here at the 10-metre winds, the burnt area in grey, and the heat flux in the shading. And you can see in the simulation that we had northwesterly winds, pretty strong northwesterly winds, ahead of a typical southerly buster, southerly wind change in the early afternoon along the coast. You can see the coastline just in the bottom corner on the right there. The background northwesterly winds are around about the 20 to 30 kilometre an hour mark, but those underpredict the observed fire behaviour. But when you look at the fire modified winds, you can see that at times they reach around about 80 kilometres an hour. And as we just talked about with the Wooroloo fire, that's because you've got the elevated above surface winds interacting with the fire plume and coming down and accelerating the surface fire. On the day, there was quite a lot of spotting that occurred. We've got limited objective data on that, so we've got limited inclusion of spotting in these simulations, but we did include one spot fire that was derived from spark simulations that RFS ran. So we know that it's a limitation of the simulations, and the accuracy is the amount of spotting that we can put in, or that we did put in, but we have developed a way to include more spots, and we're thinking about more systematic ways of doing that in the future. So you can see in the simulations that the fire modified winds get up to 70 to 80 kilometres an hour, those black arrows, really, really fast winds, obviously. And the different fires have got different faster runs in different time intervals as well. And you can see, I'll just let this run one more time through, this sharp southerly change, which really changes the active edge of the fire. And then you've got accelerated fire spread behind the change. So looking more closely at this wind change surge, and it does seem consistent that at least some of the fatalities that occurred may have been under the influence of this southerly wind change. We had really rapid spread of the southern fire front at around about 1 o'clock when the very shallow density current wind change went through, and in particular when it went through the Yatta Yatta area. So in those three plots at the top there, we're looking at the purple inset box down the bottom, zooming in on the fast fire spread run as the wind change went through Yatta Yatta. In these, our simulated fire spread reached 12 kilometres an hour for a short period, so really fast fire spread, and that was driven by near surface wind speeds that were simulated up around the 80 to 86 kilometre an hour mark. We can also see in the plots, and I've marked it in the central plot there, that a vortex developed near the leading edge of the fire front, and we've been doing quite a lot of work with RFS over the last several years trying to understand these fire-generated vortices because of the impacts that they have on fire grounds. And we're now consistently seeing them showing up in the high-resolution simulations, so there's an opportunity to learn more about them. Now, some of you may be familiar with the work of Phil Cheney, Jim Gould and Lockie McCoy back in, I think it was the late 90s, and they named this zone on the fire flank when a wind change goes through, the dead man zone, for obvious reasons. It's the area that you don't want to be in when a wind change, particularly which in Australia from the northwesterly to the southerly wind change, it's an area of great risk on a fire flank when a wind change goes through. And of course, we always want to look at what's happening above the surface. So this is a cross section of the fire plume. It's a region which is really difficult to take observations in. So the simulations give us a lot of information that we wouldn't otherwise have access to. The green line in the inset plot, hopefully you can see it going through the fire perimeter, is the location of our cross section. And you can see hopefully that it's just ahead of when the southerly change is coming through. The red shading is the updraft, and the updraft speeds are around about 16 metres per second with a strongly tilted plume. So those updraft speeds are consistent with what we'd expect to see in a small to medium-sized thunderstorm. So the red is our updraft, the blue is our downdraft. So you can see the downdraft at the top of the boundary layer. The green and the yellow shading is cloud liquid water and cloud ice water. And the black lines are showing us potential temperature. So the cloud that we can see in the green and yellow shading is around about 5,000 to 7,000 metres. That's Pyro Q. It doesn't get through the -20-degree isotherm, and that's consistent with what was happening on the satellite imagery on the day. So while there were a number of Pyro CB over southeastern Australia, there wasn't one over the Conjola fire, and that's consistent with the simulations that we've done. And we can see the really shallow cold density current coming in. You can see that's only a few hundred metres deep, and that's cutting off the plume at subsequent time steps. So a lot of detail in those plots. So how do we use this information? How can fire agencies use this stuff? And it's all knowledge that can improve situational awareness and safety at fire grounds. So our simulations at 100 metres show the local variability in wind speed and direction, both temporally and spatially. And just as a communication tool, this is incredibly powerful for people who are on the ground and experiencing different winds to what their colleagues just a short distance away might be, and also really rapidly changing winds. So we've seen that different parts of the fire line can experience different wind regimes simultaneously, and just small shifts in wind direction can change the active fire flank. We can also learn about the synoptic wind changes and how the density currents associated with those changes can accelerate local fire spread. And we've learned a lot through these simulations about the nocturnal low-level jets, downslope winds, and also plume interactions. And that's a mechanism for overnight fire activity, which of course has great risk. We can also learn about the fire coalescence of adjacent fires and the risks and the hazards of being located in between those adjacent fires, because you're not going to see the environmental winds, you're going to feel the fire modified winds in those zones. And we've learned a lot about pyroconvective cloud, plume structure, and the winds and the updrafts, and also the heat flux threshold, how much heat or how much energy needs to be generated by a surface fire in a certain environment in order for pyroconvective cloud to develop, and what depth is it going to get to. So last slide, why are these case studies valuable? Why do we do them? As we heard from Laurence and Agnes, because learning from these events improves our knowledge and operational decisions next time. I think particularly the Wooroloo simulations went through the Swan Valley. These simulations give us fascinating insights into local scale processes, which we don't really get from any other data sets. And this work has come from nearly a century of collaboration in operations and research between the Bureau and the Australian fire agencies. So this hasn't been a short project. This project really sort of builds on almost a century's worth of collaboration. And I think it's worth noting that, we've now done 100-metre resolution at 1-minute time intervals in Australia using our NWP systems. And it's the fire agencies that have led that innovation and really provided the funding and the support for high resolution modelling. And as I said, there's a huge range of other applications across the country that we could put this work in context for. People always want to know are the simulations right. All models have got strengths and limitations. It's how you use them and how you interpret the data that adds value. And another question is, can the framework be run on non-fire weather events? Quite easily. We just turn off the fire component and we can run either 300 metre or 100 metre simulations for anywhere in Australia. And if we've got the right initial conditions, in theory, we can do it for anywhere in the world. And as a proof of concept for that, as part of the project, we've also run a case study on the Adelaide 2022 thunderstorm and mesovortices event. And we've got some incredibly detailed simulations of some of the thunderstorm indices at that event. How much does it cost to run a simulation? I only asked this question reasonably recently, and the answer is it's less than $1,000 to do a high resolution computation on the supercomputer for a 24-hour period, which I think is a really, really small amount of money just to do the computational aspects. By comparison, the investment in Australia in climate simulations is of the order of tens of millions of dollars, but we've only recently got to the point that we can do these kinds of high resolution simulations for this kind of money. So it opens up a world of opportunities. Historically, it has taken time to collect the data and analyse the simulations, but with the framework that we've developed in this project, it should be faster in future, and we will get faster with practice in terms of doing case studies closer to real time. So we've developed a framework for rapid turnaround case studies. We've got reports and papers in preparation and the detailed case studies of both the Wooroloo and the Currowan fire. And we do have, or NHRA are hosting 2 online extended seminars on each of the fire where we'll go into much more detail on the data, the observations and the simulations of each fire. So those are coming in the next couple of months. In conclusion, I'd like to thank NHRA and also the fire agencies for all of their support of this project. I think one of the questions is how do we use this case study framework in future? Thank you.
Thank you, Mika, Agnes and Laurence. Great presentations. We've got some good questions. You've already covered off on what's next, Mika, so I don't need to ask that question. Appreciate that. We'll start with the first question from Shima to Agnes, asking if you could explain how the fire behaviour modelling is done in Western Australia. Is it through manual calculations or a program or AI?
Yeah, we've got multiple, ways. Basically, we have our Aurora Bushfire Simulator that we develop in the state and continually improve every single year. So that's a program, and we also do manual calculations, but we haven't ventured into the AI yet because there's just so many uncertainties, and yeah, maybe in the near future.
Thanks.
But sorry, I forgot one more thing. We do have Spark as well as a backup to Aurora.
Awesome. Thank you very much. We've got another question that I think Mika has answered, which is how can we obtain access to these case studies and resources for training and education purposes? Rodney will be doing some further knowledge sharing forums, one on each of the case studies, and all of the materials from the project will be available on the website, on the project webpage, probably before June this year, I'd say. We hope to publish them online, so that's how you can access them. And a link to that webpage, that project webpage, I'm hoping Oscar might be able to put that in the chat and you could bookmark that for your future reference, because we'll add resources to that as the project progresses. Now, this is an interesting question from Tony Marks. How does this model, the Access Fire model, correlate to Phoenix and Spark? He notes that they're the F-band tools in use now. And does Access Fire make a third modelling tool? Mika?
Access Fire is a third modelling tool, I guess a third fire simulator. But the distinction, of course, is that Phoenix and Spark both take surface fields. Spark does take some limited 3D fields, but you don't capture the fire and the atmosphere interactions. So they take weather inputs to drive the fire spread, and there's no knowledge, I guess, or no understanding of the atmosphere that's a fire there emitting a heat flux. And I think anybody who's been on a fire ground or seen any imagery, we know that when you've got large fires, they change the surrounding atmosphere. So that's what's captured in Access Fire. The distinction, I suppose, from a research and operational point of view is that historically it's taken us a lot of time and effort and computational cost to run access fire, so it's not available operationally. And obviously Spark can be run for multiple fires very, very quickly, which we can't do for access fire. So one of the things that we're working on at the moment is how do we take some of the knowledge that we've got from the 3D modelling and apply that, probably using parameterizations in more computationally effective ways into Spark and Phoenix. So it's been good. We've been working with RFS with Spark on this project and talking to the AFAC team as well. And I think using the two modelling systems in combination moving forwards is probably a good way to go.
And it also goes to that collaboration, doesn't it, across at fire management agencies and the Bureau during events. Yep, during live events.
And I think as well, it kind of goes back to what I think is more the US approach. That is there's not one model that's right or wrong, but there's different modelling frameworks, which are different tools in the toolkit, if you like, and figuring out how do we use that combination of tools to best effect is one of the things we need to do moving forwards.
Yeah, Nicola, I'd add to that and build on what Mika's suggesting, is that these case studies provide us an opportunity to understand the strengths and limitations to the models for application into operations. And so this is one of the benefits of this project, is that we're not only building the capability of being able to run this coupled fire atmosphere modelling for the Bureau, but we're also understanding the limitations and potentially where they're best applied. And that's the job of the fire behaviour analyst, to have the knowledge of the strengths and limitations of each of the models and apply these models in context. That's what I'd say.
Thank you, Laurence. Agnes, did you want to jump in at all?
Absolutely. From our side, if you have different models that are saying the same thing, that just increase your confidence in what the fire is going to behave. So unfortunately, not all fires are simple. Lots of them are actually quite complex. So having multiple models that can back up each other, it gives us, as a state FBAN, more confidence in what we need to do.
That's awesome. Thank you all three to addressing that question. We've got a detailed question relating to the Currowan fire. But I think it's from Jason. Jason, we might hold that over to the next knowledge sharing forum on that fire, because that gives an opportunity to go further into the technical details for the actual case studies themselves, because we've got quite a few questions here. So I hope you don't mind, Jason, but we'll keep that one for the knowledge sharing forum. In the absence of perfect modelling, what should practitioners prioritise observing in the field to validate or challenge what the model is suggesting? Would be helpful for future case studies.
I'll answer and then throw over to Laurence. It's kind of interesting because a lot of the work that we've done with Access Fire, we haven't been trying to get a perfect model or a perfect representation of the actual fire spread. We've really been trying to understand the processes that are driving the fire behaviour, and that's been the motivation for a lot of the research work. I will say that one of the things that's been fantastic over the last several years, particularly working with RFS and with DFES, is that they've provided a lot of their fire reconstruction data to us, and also a whole collection of incidental pieces of incidental artifacts, like the photographs that people take, the images that they take on their mobile phones. Some of the videos that we have are really incredibly valuable as verification or informal verification on what the model is showing and what's happening on the actual fire ground. And I think one of the things that I've found interesting over the last 15 years or so that I've been doing this work is that we see features in the model, and you go out and you talk to people who are on the fire ground, and we can always reconcile what's happening in the model with what was happening in the fire ground, which gives us confidence in what's happening, even though we don't necessarily have the objective data to do a really formal verification. One thing that we would like to be able to do, and we've got plans hopefully to do this, is to put mobile radars where you get really detailed high resolution wind fields out near a fire. Obviously there are safety issues in terms of how we can do that safely, but that would give us wind fields that we can then run a coupled fire atmosphere simulation on and then do a more formal verification. But all of the data that gets collected on fire grounds, and I think particularly things that people take like photographs and videos can be really, really valuable in trying to reconcile the simulations and what happened.
Mm-hmm. Mm-hmm. Laurence or Agnes, did you want to add anything to that?
From my perspective, we take a range of I mean, there are so many ways that we can validate fire behaviour and collect information, ranging from remote sensing down to field observations. And so, you know, from a fire behaviour modelling perspective, it's really important to understand where the fire is at certain periods of time, and we can use various sources to, I guess, you know, verify each of the sources of information to ensure that we've got an accurate picture of what's going on. So fireground observations are critical, but as are the other remotely sourced sources of information, as are things like aviation and line scans. So there's a host of field verification techniques that we use, and perhaps we can take that offline. Yeah.
Thank you very much, Laurence. We might move on to another question. And this question from Greg is, how much does terrain topography contribute to local weather effects in the modelling?
The answer is hugely. And I think one of the things we're seeing, particularly from the Western Australian cases, is that you don't need high topography or complex topography to drive really complex fire behaviour. And you may remember the Margaret River fire or the Ellenbrook fire. That was back in, I think it's 2011, where it was quite a small hill that generated some really interesting winds. And then, of course, when you've got a fire plume in there, then that changes the wind regime as well. There's a lot more work that's been done on terrain topography in the United States, and they've got much denser networks of automatic weather stations out there looking at mesoscale mountain meteorology. But I think, you know, one of the things that's come out of this project, which I think is just fascinating, is what happens when you do a high resolution simulation at 100 metres over not particularly complex terrain. But I think, again, the thing there is that it's producing everything that we would expect to see. So we're getting the flow in the valleys that we'd expect to see from the observations that are available. We're getting the flow on top of the topography that we'd expect to see. So obviously there's room for more verification. And yeah, obviously opportunity now to look at a whole range of different cases, not just in fire, but things like, you know, wind farms, for example, or agriculture. There are applications there for looking at the detailed flow of the terrains.
Thanks, Mika. Folks, we've got 1 minute left, so we've got lots and lots of questions. This hour has just streamed past so quickly. We will keep those questions because we will use them to inform the knowledge sharing forums that we're going to run on each of the individual case studies. But at the moment, I just wanted to thank Mika, Laurence and Agnes for taking time to share this work and their perspectives on it and in answering what questions we got to today. I'd also like to thank everyone who joined us online and for submitting questions to the panel. The recording of this webinar will be online in the next week or so, and all of you will receive an email with a link alongside information about our upcoming hazardous webinars and hopefully some information on the extra knowledge sharing forums we're doing on this project. We'd also like to mention that our annual Natural Hazards Research Forum is coming up soon, running from the 10th to the 12th of June in Adelaide at the National Wine Centre. Registrations are open and there's a link to more information on our website homepage. So that's just naturalhazards.com.au. And for everything Natural Hazards Research Australia, please sign up to our newsletter and follow us on social media. Thank you everyone for your time this morning, and we will see you next time. Cheers.